Hello everybody and welcome to another JASP tutorial. Today we are going to do independent samples t-tests, and I'll go ahead and link you to my other t-tests just in case you accidentally hit on this one but you need paired or one sample t-tests. Now for this, as always, I am using the JASP 0.10 preview release version, and let's jump right into it. For the data, I'm going to go ahead and open a data file that I have been using in a ton of these videos. It's a data file from about 5 years ago that I can use to play with. So we are going to jump right into the independent samples t-test. So we go to t-test, independent samples t-test, which brings up the options window and the results window. So what I wanted to do for this one is just take very simply the grouping variable of gender. I'm going to go ahead and select my gender. Now you can see here this box accepts nominal and ordinal level variables, and so I'm just going to go ahead and plop gender into the grouping variable. And depending on what you are testing, you can go ahead and put in any number of scale or continuous variables into this box, and it will run through gender as the grouping variable. Now, the grouping variable is extremely important for independent samples t-tests to only have two levels, a 0 or a 1 or a 2, or however you've decided to code that. If I go back to here, I have 1 and 2 for my genders. I haven't really marked what those are. I can go ahead and label them. I'll go ahead and label 1 as male and 2 as female. For everybody listening at home, I'll go ahead and click on male so I get female loaded in, and go ahead and close that, and you can clearly see I've got male and female marked on my spreadsheet. So I go back here, and again, gender is then going to come up as male or female in my output, which is extremely important. Now, I can choose any one of these test variables. I don't have any specific hypotheses, except for that there will be a difference. I'll talk about alternative hypotheses toward the end of this video. So a null hypothesis is that there's no difference between men and women, males and females, on, let's say, their accuracy on conflict problems. So that's what this variable is. I'm going to go ahead and throw that into the DV area there. And it's going to run through the t-test, and as you can see here, it's not looking good for the myth. I'm just kidding. Yeah, that was a little Mythbusters humor for you. I have a t-value, a degrees of freedom value, and a p-value for my student's t-test. Now that's the first option that we can choose. It is the default that JASP chooses for you. Now there are two different additional tests that we can run. But we'll determine whether we need to run those tests for two different reasons. And I'm going to go ahead and jump to the assumption checks, because independent samples t-tests require two different assumptions that we haven't seen in the previous two videos, one sample t-test and paired sample t-test, and that is equality of variances. So we've seen normality. This determines whether or not males are normally distributed on the DV and females are normally distributed on the DV. We have the Shapiro-Wilk test as previously seen. It gives a W value, and this W value is an indication away from a typical value for a normal distribution, which then gives us a p-value. That p-value is based on an alpha that we have chosen specifically for this assumption check, 0.05, 0.01, 0.001. Anything less than whatever that alpha value is going to indicate whether or not you have an issue with normality. it's important to note that you should use the same alpha value for your two groups on the same variable. So not 0.05 for females and 0.001 for males. We're not going to go ahead and do that. We're going to choose 1 for this particular test of normality. So it just depends on how liberal or conservative you want to be in violation or deviation from normality. I think it's clear to see here that we probably don't have an issue with males, but we definitely have an issue with females' accuracy scores on the conflict or incongruent items. It's again, this p-value is comparison to an alpha value that is not the same as the test alpha and p-value comparison. We'll definitely keep 0.05 over here. I mean, it doesn't really matter. It's got a p-value of 0.36. I think we're in the realm of no difference there. Failing to reject the null on that one. But I also wanted to add in here that equality of variances. And so this brings up Levine's test of equality of variances. And it determines whether or not males and females have the same variances. Because one of the assumptions of t-tests and independent samples t-tests specifically is that I should only be comparing two groups that have equal variances. And if I don't have two groups with equal variances, I'm going to have to make an additional choice about what tests to use, whether it's students' t-test, Whels, or the Mann-Whitney test, as you can see here. So we get Levine's test, and it gives us an F value. F might be familiar to those who have done ANOVA, analysis of variance, before. We get a degrees of freedom, which is 1, because there are two groups. So 2 minus 1 is 1. So we get an F value, a degree of freedom for that F, and what that P value would be with those corresponding values, and we get a P of 0.134. Again, the alpha we use to compare this P value to is and can be different from the p-value for the actual test. Generally speaking, I would use the same alpha that I used for my normality checks, because you don't want to be going all over the place with, well, I'll have my alpha for normality at 0.05, but I'll have my equality of variances alpha at 0.001. And it seems kind of shady, seems inconsistent about what you're doing. And your assumption checking. So at any level, though, I don't think we have a problem with equality of variances. And so this p-value does not enter into the realm of quote-unquote significant results, as you can see from the note for the test of normality. And so this p-value suggests that the variances for males and females on this particular DV, conflict problem accuracy, they're equal. Those variances are, generally speaking, equal. And before we jump into the other additional statistics, to clear this up, I'll go ahead and throw in descriptives, and we can see that the standard deviations, which is a measure of variance, are fairly similar, 0.28 and 0.33 or 0.328. So they're pretty close to each other, which, just looking at those descriptive statistics, tells us that the equality of variance is probably not going to be an issue. But what I did want to point out, bringing up the group descriptive statistics, is the N. And when you have either unequal variances or unequal N's, more than, I would say, a difference of 5 or so, and that's essentially arbitrary. The fact of the matter is there is a 13-person difference between males and females in this sample. So we have a problem because another assumption of the student t-test is that you have equal groups to test on your DV. And so that's where Whels test comes in. Whels test is essentially the same as the student t-test, but it incorporates that difference in the end. So one group being larger or smaller than the other. And you can see there are slight variations. So the test statistic is a little bit higher for Whels in this case. My degrees of freedom decreases because I have to get rid of some of those degrees of freedom that contribute to the unequal group sizes. And then based on the changing degrees of freedom, my p-value changes. Okay? And so you can see here that an increasing test statistic, a decreasing degrees of freedom value, leads to a decreasing p-value by 0.02, actually less than 0.02, 0.016. And so not much changes in our decision making, but if I were to report this in an APA style paper, I would report Whels test for the fact that I have a 13n difference between my two groups, even though the equality of variance is not a problem. It's also that it's also important to potentially use Whels test here because the female group has a deviation from normality in this case. Okay. Now, if there were issues with both normality and both equality of variances, I'm going to probably have to use the non-parametric test that's available to me in JASP. Now, this last test is called the Mann-Whitney U test. You might have seen it in other programs as the Mann-Whitney U. You get a U instead of T. I'll go ahead and click that, and that gives me the U value, the 537 here, and the corresponding p-value for that. You might actually see this as the Wilcoxon-Mann-Whitney test. Wilcoxon is a part of this one, but lots of times. So if you're a migrant from SPSS, this would have been the Mann-Whitney U, and so you end up with the test statistic and the corresponding p-value for that test statistic. So the U and its p-value, as you can see, they're all fairly similar to one another. But this Mann-Whitney U is the non-parametric test for ordinal pairs. So if you've got an ordinal pair here, or you run into issues with your assumptions, you would have to report the Mann-Whitney U. Okay. So just going to go through the additional statistics. So location parameters, this is the mean difference for student T and Whels T. It's the mean difference. Okay, so it gives you the mean difference between the two. And the Mann-Whitney U gives you the Hodges-Lehmann estimate. And we get a standard error for that mean difference, which is always a lovely statistic to get because there's potentially some uncertainty with that mean difference. And you can then go back to this 0.60 and this 0.526 and see that if I subtracted the one from the other, I would come up with a location parameter similar to that. I can also get a confidence interval for that location parameter. It gives me one side or the other for this value, the upper and the lower limit. I can also get the effect size, and as the, I'm going to go ahead and drag this over and just get the line there. Nope. Can't make it bigger. Well, let me make it bigger. Well, that's unfortunate. So for the effect size for student and Whels tests, Cohen's D is given. Mann-Whitney U gives you the rank by serial correlation, which is the non-parametric ordinal and nominal correlation value. So 0.238 or 0.24 for Cohen's D, so smaller than the small effect size signpost, I'll say, of 0.3, so it's quite a small effect. Regardless of what the p-value is, there's not much difference between the means, as you can see on the scale. And then it's a very small positive correlation between the two groups, males and females, for that. And we can also get confidence intervals for our effect size, and you can see those there. We can get descriptive plots. The descriptive plots will essentially be a line graph for the two groups, dot for each group, and that is the value, that is the mean value 0.6 and 0.52 for these two. Again, the y-scale is automatically generated when you throw in the confidence interval of 95%. Again, these are not standard error bars, these are 95% confidence intervals. Okay. And again, I'm going to exclude from this tutorial the Vogt-Selke maximum p-ratio. If you are interested in that description, you can click the I button here and open up the JASP help window, and it will tell you everything you need to know about it. Here's the Vogt composite here if you'd like. All right. Missing values, again, exclude cases, analysis by analysis. That would be whatever variables you have in here, depending on what variables have missing values. That'll go there. And exclude cases list-wise. Any person having any missing value in any variables being run through as DVs will get excluded from all analyses, as opposed to just the analyses where their missing values are. I hope that makes sense. Okay, finally, let's talk about the alternative hypotheses. So for independent samples t-test, the null hypothesis is that the groups aren't different from each other. And so the alternative hypothesis that is antithetical to that, of course, is that they are different from each other with no direction to that difference. So by default, that is the alternative hypothesis that JASP chooses for you. Group 1 does not equal group 2. These are radio buttons. Only one selection can be made per independent samples t-test. And so this gives the output that we are currently looking at. So group 1 does not equal group 2 is my alternative hypothesis. That doesn't seem to be the case based on this p-value, and so fail to reject the null hypothesis. But if we said, you know what, I think the literature suggests that males are going to be better than females at this task. And so I'm going to go ahead and say it's group 1 is going to be greater than group 2 as my alternative hypothesis. And that is a one-tailed test compared to this two-tailed test. So instead of my alpha being 0.025 in either tail of my t-distribution, I'm going to go ahead and put 0.05 as my alpha in one side or the other. This is the right side, and this is the left side of that t-distribution, where I'm going to find my t-critical value. So if this one is males are going to be better than females, and this one is females are going to be better than males. And so, or males are going to be worse than females, actually, I should say. Apologies. So I'm going to go ahead and select the radio button that males would be better than females at this. And you can see here that my p-value changed. Now, it's not so much that we have to worry about the test statistic changing. That's not going to change, because the degrees of freedom and the numerator haven't changed. But what has changed is where I find the p-value in the t-test table, based on the statistic and the degrees of freedom, or the critical value. And essentially what happened was that, and you can see here, that when I do that, it's 0.36 with no with not equal to. It's 0.18 for equal to. So a one-tailed t-test effectively divides your p-value from a two-tailed t-test in half. And so you can quickly see that. Now, if the assumption in the literature, and this is, I believe, why IBM and SPSS still do it this way, is the default is a two-tailed test. The default is a two-tailed test. It makes it more difficult to detect an effect. You're more conservative on whether or not you've detected an effect. And so, if somebody is going to do a one-tailed test in a report, an APA report, they need to indicate in words that the p-value is from a one-tailed test. Because then you can multiply that p-value by 2 and get that p-value for a two-tailed test, which is very important if you are assessing the effect or non-effect for a t-test that is being reported. So now I'm going to go ahead and click on the group 1 is less than group 2, which will essentially give me males do worse than females. And again, the thing that changes is the p-value associated with the test statistic and the degrees of freedom that aren't going to change. And so, again, if I have not equal to, you see my p-value is 0.36. If I multiply that by 2 because I'm going in the opposite direction from what the data are actually doing, because men in the sample did not do worse than females. Male is less than group female. This is more wrong. It's doubly wrong than when I was just doing not equal to, because 0.36 plus 0.36 is 0.82. So we can multiply our p-value by 2 in order to get that p-value in the wrong direction. So this is an extremely wrong outcome based on the observed data. Now again, and I'll go ahead and throw up the proper notation for this independent samples t-test in APA style. You'll see it somewhere on the board here. But what I want to end with is suggesting that for independent samples t-test, I would just leave it on not equal to if you don't have a directional hypothesis. And again, directional hypotheses need to be indicated and grounded within the literature. You have to have some evidence that for making that directional hypothesis. And I would say even with a directional hypothesis, nothing's wrong with using a two-tailed test. Again, it's a little bit more conservative to detect that effect. So yeah, that's a independent samples t-test in JASP. Please leave your feedback and comments down below. Thank you for joining me and watching this video. Bye-bye.